Mr. Robinson.
Hey, how's it going? Sorry to be late to start. I totally like made the class and I started the stream and stuff, and I was sitting around and I was like, oh, that's weird, nobody's joined. Usually there's like 2 or 3 people in the waiting room by the time class starts. And then I realized I hadn't posted the link because I'm getting senile in my old age, apparently.
Hello.
Hello, how's it going?
It's going
Good.
Yeah, how's work?
Cold brew.
Rachel, this is going to work.
You made cold brew?
Yeah, I made your cold brew with your like recipe.
How'd you do it?
I didn't have the like thing you had, the contraption or whatever, but I just got a glass jar and I put the coffee in a cheesecloth.
Hey, I'm glad you say that. I was so glad that you said cheesecloth and not some like inferior cloth. Yeah, that totally works too.
Yeah, and it was really good.
Tight, yeah. 2 days, 1 day at room temperature, 1 day in the fridge.
Yeah.
Tight.
Very good.
Also, the other thing that you can do if you want to spice up your cold brew, the recipe that Starbucks uses for their vanilla cold cream is actually hella easy. You just take heavy cream, or if you don't have heavy cream, half and half works. And you basically do 5 parts cream, 1 part simple syrup, and then 1 drop of vanilla extract. And you really do have to measure it with a drop because vanilla extract kicks if you use too much of it.
Oh, yeah.
Yeah, so a good way to measure it is to just like dip a spoon in it and then use the tip of the spoon to bring over just 1 drop. And then you whisk it left, right, left, right, left, right, not around in circles or whatever. And it makes a delicious
Wow. Fancy.
Yeah, it's like I am a mostly very frugal person. Student loans will just kind of do that to you, but just because you're living as cheaply as you can, it doesn't mean that you have to sacrifice that much quality of life. It just means that you have to learn to do stuff on your own.
There you go.
Anyway, welcome in everybody. Welcome back to some of the funnest education, simply because it's low stakes. You only have to take away from it what you want to take away from it, and at no point will I test on any of this stuff. I just want to make sure that you guys have a good foundation for the stuff that you're going to deal with next year. And of course, if you ever need help in the coming years for anything, either just like general advice or physics help, hit me up. You all have my personal email, right?
Yeah, I think so.
Yeah, it's I don't want to put it up on YouTube. I'll post it in Google Classroom at the end of this lecture so that you can all get it down. And some people do wisely take me up on that offer even years down the line. There's actually 2 alumni from AGBU MHS who graduated. One of them graduated 3 years ago now, and the other one graduated 4 years ago now. And now that both of them are getting to their respective med school application times, I've been helping them out with the physics section of the MCAT. So if you ever have a physics issue in the near future, let me know. Nonetheless, today we're going to talk about wave mechanics, but really just big picture concept stuff. No math at all, just the interesting tidbits. Somebody better than me can teach you the math in a few years. And the point of this is so that we can talk about the extreme ends of the physics spectrum, all of the stuff that we're working on now. Because if you end up doing science or engineering for a living, the work that you end up doing is on the cutting edge. So even though we have to teach you all these fundamentals from 300 or 400 years ago, because that's what all this stuff is based on, it's still important to be conceptually aware of what's going on at the edge. Because if you're going to participate, if you are going to follow after me and do the work, this is the stuff that you need to be versed in, not the stuff on the AP test necessarily. And this isn't just me like flexing my sunglass collection. After lecture is over today, or towards the end of it, I have a demonstration to show you guys with these sunglasses, because people always treat quantum mechanics like it's some sort of impossible to understand phenomena. And as a result, oh, weird, you can see my reflection in the glasses. And lots of people, because it's so poorly understood, they use it to justify all sorts of nonsense, like quantum healing, or this crystal will heal you because of its quantum vibrations, or all of these abuses of the word quantum mechanics, when in fact, even though it is extremely difficult to understand. Just because it's difficult to understand doesn't mean it's impossible and doesn't mean it's necessarily magic. It is one of the most important theories for the underpinning of our technology today. So always keep in mind, whenever you think about quantum mechanics and how weird it is, you wouldn't have a computer without it. It is a necessary technology to make the modern computer chip go. And lasers wouldn't work without it. And oddly enough, I can show you a demonstration with 2 pairs of sunglasses that itself is a quantum mechanical phenomenon, which it's crazy to think that regular objects like this have quantum mechanical properties. But if quantum mechanics describe all atoms, which it does, and everything is made of atoms, then even though it might be hard to observe in the wrong conditions, every single object actually has quantum mechanical properties which are worth understanding. And I'm going to do my best to try and get that idea across within a few class periods, which of course, I've been studying quantum mechanics for the past decade. And we as a species have been trying to work out quantum mechanics for a little over a century, and we're still not quite there in terms of the theory. So know that everything that I'm going to say is just based on our current best understanding, but there are questions that have not yet been answered, which is where the scientists of tomorrow come into play, which is like your work should you choose to take it up. But nonetheless, today we're going to start off with just waves for the sake of waves, so that we have the vocabulary to understand why waves are interesting, how they're distinct from particles, and why quantum mechanics is so strange in merging the properties of the two. So this first bit, just waves. And you'll notice a lot of common logic and vocab and terms and variables with oscillators, because every single wave itself is an oscillator. Here's the primary difference between our treatment of the two. Normally an oscillator is fixed in space unless you're doing some sort of high-end graduate problem. So if you're a graduate student, you might get a fun problem like, here's a pendulum, except the pendulum is on a carousel and the carousel is spinning. So how does the pendulum behave as it's being whipped around by this carousel? That's not what I'm talking about, like a moving wave. Normally, if you have a spring mass, it's just going to do this. Or if you have a pendulum, it's just going to do this. Waves do the same thing. They really just oscillate back and forth. The only difference is that something about their motion translates forward through space as they vibrate. This is called a traveling wave. And traveling waves are much like the equations of motion of our oscillators, in that normally they're either modeled as a sine or a cosine, or the sum of a sine and a cosine, so that they satisfy that same fancy differential equation that regular old oscillators do. The idea that because of this physical scenario, this thing's motion is proportional to its own second derivative, and the family of functions that have that property are very limited. It's really just sine or cosine or e, which you guys will learn in higher end math, that you can rewrite those things as each other. Sine, cosine, and e are all actually the same object, just viewed from different perspectives. But nonetheless, when it comes to traveling waves, we have this idea that they do this. And there are, that's a funky wave. And there are some physical features that we can affix to this wave. What are some of those physical features that we remember from AP Physics when we were talking about graphing oscillators?
Like the period?
Yeah, so it has something called the period, capital T, which is the amount of time for one complete oscillation. So that is to say, the amount of time that it takes an element of the wave to go from here to here would be the amount of time involved with one period. But if this is actually lengths that we are measuring out, what do we normally call this length? The length of one wave? It's a trick question. The length of one wave is just one wavelength.
Okay.
So we also have lambda, the wavelength, which is what you would get if you took a wave, and GTH, That is the length of the wave that you would get if it was a wave that you could somehow measure with a ruler or some sort of measuring device, or in a lot of cases, we measure waves by trickery of their properties, which is a demonstration that I'll show you guys tomorrow. And based on these two terms, there's one more thing that we need to parameterize this guy. What's that third variable that's independent from these other two?
The height?
The height. And what's the special name that we give the height?
Amplitude.
Oh, yeah.
Amplitude. Yep. So this thing here is A, the distance from 0 to its peak, where A is just the height of the wave, the amplitude. So all of that vocab from oscillators is the same. Here are some slight differences. There are two different types of longitudinal, or sorry, there are two different types of mechanical traveling waves that we can differentiate, and it all depends on the type of motion that is driving the wave forward. So if we imagine that this whole wave is made of a bunch of physical elements, there are actually two different ways that we can drive this wave forward through space. Either the individual particles can vibrate left and right, and you know what? If I hope I brought home my Slinky. Let me see if I have my Slinky. Let me go. I'm gonna be right back.
Okay.
Heck, I left my Slinky at work. Big sad. Oh well. Slinkies are really good for this because you can show both types of waves on a single Slinky, depending on how you generate the wave on it. However, when it comes to the two different types of waves, we have longitudinal waves and we also have transverse waves. So I'm going to color code it. Longitudinal versus transverse. And this has everything to do with the motion of the particles creating the wave versus the motion of the wave itself. So if this mechanical traveling wave is going from left to right, I could say that this is the velocity of the wave itself. So I'll call that velocity sub W. However, the direction of the motion of the particles can either be parallel to the wave's displacement or perpendicular to the wave's displacement. In the case that it is parallel, which is to say that the velocity of the particles is parallel to the velocity of the wave. Oh, heck, I said I would color code it. Let's go ahead and make the longitudinal arrow on here purple. That means that if the wave is traveling left to right, each one of these little particles is vibrating left and right. Each one as it goes through the wave is getting compressed together. So this would be, and I know imagination stuff sucks, but this would be, imagine if you will, I had a Slinky, and to set a wave across it, all I do is I take one hand and I vibrate it. And it's gonna send a little pulse through the rings of the Slinky until it reaches one side, and then it bounces back. And then in the case of transverse waves, this is the case where the velocity of the particle is perpendicular to the velocity of the wave. So this is to say that instead of these individual particles vibrating left and right, each one of them is actually vibrating up and down as the wave travels through them. So this is probably the type of wave that you make on a Slinky when you're a kid, where you take one end and instead of shifting it left and right to create a little vibration that goes through it, you take one side and you shake it up and down, and you can actually see a sine wave pulse through the Slinky from left to right. I bet I can find a quick video of this. Give me 1 second. Called it. Yeah, you just Google transverse longitudinal Slinky, and the first hit is, oh my God, YouTube is so loud. Okay, I just deafened myself with this guy's voiceover. Anyway, so we have a bronze Slinky here, right? And so right now it's laid down flat on the table. And so when he brings his hands together, you can see how the Slinky chain itself kind of packs together. And so that type of wave that he's doing right now, where he shakes it up and down, that would be our transverse wave. The coils move up and down, but the wave travels from left to right. Or here, where he's just pushing it along, kind of making one little high density area of rings, and then that expands through the Slinky from left to right. That would be our example of a longitudinal wave. Is that okay? There we go. Yeah, longitudinal waves. Okay. And for the most part, the properties of these waves are not significantly different. It's important to draw that distinction, but just for your own information, one of these is a water wave, one of these is a sound wave. Anybody want to guess which is which? I think it's easier to figure out which one is a water wave.
Probably the transverse.
Right, if you think about the surface of the water, it moves up and down as the wave goes through it left to right. So water waves are transverse waves, and sound waves are typically mostly longitudinal. Now, of course, nothing in science is easy, so technically both have properties of both. But for the most part, the motion of a water wave is almost entirely up and down. There's a little bit of left-right, so it has a weird circular motion to it. And with sound waves, it's mostly longitudinal, though there is a little bit of rarefaction up and down to it. Now, here's what's interesting about waves. Aside from this stuff, this is all good. They typically have a fixed velocity. And this is the same equation that we derived before, where if there's no acceleration, velocity is just equal to distance divided by time. So we could say that this is lambda divided by the period t. Or what was that thing that we had, that thing that we could call 1 divided by period? There's a substitution we can make for 1 over t.
Was it the frequency?
Excellent. Yeah, frequency is reciprocal period. So frequency is equal to 1 over period. So this can also equally be written frequency multiplied by wavelength. So for most waves, waves travel at a constant rate through most mediums. That is to say, the speed of a wave through water is basically constant. The speed of a wave through air is basically constant. The speed of light is literally constant itself. And so because this thing is normally held fast as a constant, this gives us the relationship on the right-hand side, that the higher the frequency of a wave, the lower the wavelength. And the lower the frequency of a wave, the higher the wavelength. As a result, these two things are not typically independent parameters. They are the same thing. If you have one and you know what the speed is for any given medium, you can use that to calculate the other, and vice versa. And so let's go ahead and look at a quick view of a wave. So here is a wave in water, this little simulator here of water dropping slowly into our sink because we already filled up our cold brew pot and forgot about it. And now it's overflowing and the sink is filling with water as it continues to drip one at a time. And you can see here that this is our source and this is driving a wave as it goes outward. Is that okay?
Yeah.
Now I can increase the amplitude, I can make the drops more massive effectively so that the disturbance is greater, or I can speed up the rate at which the droplets come, or I can slow down the rate at which the droplets come. All of these are manipulables here. But this is cool, not because I am interested in this view of a wave, though this is a good one to have. This is fine to see how the wave propagates from left to right. But how to interpret this top view. So this top view is really what we're here to talk about today. And this is to say that in this view of things, the light blue part represents the top of a wave, the crest of it, and the black part represents the trough of a wave, or the bottom of it. And for the most part, this is what waves look like as they spread outwards radially. So when you talk, this is how the sound is spreading out around the room from your mouth. Is that okay?
Yeah.
And we'll talk more about sound waves tomorrow. That's where I'll be doing my like fancy demonstration stuff and maybe ruining my computer. I don't know. We'll find out together. But in the meantime, let me show you guys a quick video clip that I like, especially since Cosmos Season 2 is coming out soon. I'll just shill this. I'm not getting paid. I'm not actually a shill. Though if Neil deGrasse Tyson is listening out there, I'll take your money. I'll shill. I don't care. Check this out. I really like this. This is another really good visualization of waves and how they're just kind of everywhere and spreading out all the time. And I think this should, oh my, okay. I think this should have sound. Did I do it right? Does it have sound?
Yeah.
Sound waves are so beautiful to hear. Imagine how beautiful they'd be to see. You ever wondered why organ pipes have different lengths? I press a key. It sends compressed air into a particular pipe, producing sound waves. If we could slow the sound waves down a few hundred times, they would look like this. The length of the pipe determines the length of the sound wave that can fit inside it. A short pipe gives you a short sound wave. Short sound waves have high pitch or frequency. Let's stop the waves for a better look. The distance between adjacent waves is called the wavelength. A long pipe gives you a long sound wave with a low pitch or low frequency.
I'm probably gonna have to edit that out so that this doesn't get copy struck, but if I do edit it out, I'll put a link in the description so you can watch that clip again should you want to. Anyway, I like that. I think it's just a fun conceptual way to look at sound waves, and tomorrow I'm gonna show you guys a demonstration with a pipe that takes advantage of sound waves or sound in a similar way. It's basically a description of the speed of sound lab that we're sadly missing out on. But if your college is good, it's probably one that you do. It's one that I did at UCLA. Cal State LA didn't have it, but I was able to talk at enough people to where they might be adding it next year. Anyway, let's go ahead and do a compare and contrast of waves, which I know is like a weird thing to do, but they actually have a lot more in common than they have different, which is why finding a hard and fast way to differentiate them is crucial. What are some things that we learned about particles this year? What are some properties that they have? This isn't a trick question. Like, what are the kinematic terms that we describe particle motion with?
Don't they just like move around?
So if they move around, that means they have some kind of velocity. And as it turns out, so do waves. So both particles and waves, they have fixed velocities that we can calculate or describe. What are some other properties that particles have?
They like
What are
not
other things we learn to calculate? Other physical terms? What was that 1/2 mv squared thing?
energy.
Energy. Both waves and particles are capable of carrying energy from one place to another. They may have different equations, but the meaning is exactly the same. For a particle, it's directly proportional to the velocity. For a wave, it's directly proportional to the amplitude. The taller the wave, the more energy it carries. But those two things can be equated. You can show how the energy of a wave can move a particle, or the energy of a particle can move a wave. Both of those are accepted, you know? So again, let's try and find some distinctions here. What are other properties that we learned about particles? We learned to calculate velocities. We learned to calculate energies. What was that other thing, the other side of the coin from energy? Energy is a scalar. What's the vector version of that idea? So that would be, and I mean, we're gonna have to fill out this whole chart anyway. So waves have a frequency that particles don't. Just shout out some terms and we'll fit everything in here.
Speed, maybe.
Well, let's say velocity.
That kind of goes under velocity. Anything we can do with velocity, we can do with wavelength.
Is there force? Is there force?
That's really interesting. So both of these are dependent on forces, but in different ways. So if you apply a force on a particle, it's just kind of sent off in motion forever. But when it comes to forces acting on waves, there are still forces there enabling this motion. But the same way how oscillators need a restorative force, waves need a restorative force to function also. So when it comes to waves traveling through the air molecules want to be evenly spaced. And when I talk towards my computer monitor, which has the microphone built into it, my vocal cords are actually compressing the air right in front of them. And when that air gets compressed, it then wants to spread out, which causes air in front of it to compress, which then spreads out, which compresses, which spreads out all the way to the microphone. And so there are forces present there, but the orientation is a little bit different. So yeah, they're both inherently involved in discernible forces. What else?
Momentum.
That's what I was looking for. And again, the same way how particles have momentum, waves also have an associated momentum with them. This is why when you like talk, you can literally feel it on your hand if you place your hand right in front of your mouth, because the sound wave itself carries a momentum which is capable of affecting your hand. If you talked at something that had a small enough mass, those sound waves would eventually accelerate that object. And so the reason why I bring this up is that for a long time in science, we had a question going all the way back to Isaac Newton himself. What is light? Is light a particle or a wave?
A wave.
Kind of. Huh?
Isn't it particle?
Also kind of. Yeah, so both of those answers are correct and incomplete. And this is why this was a question that was asked in his time, but definitely not answered in his time. It wasn't answered until probably the last decade of the 1800s, 1890 something. We started to develop this clearer picture of what the deal was. Light has a lot of properties which are wave-like and a lot of properties which are particle-like. But the problem with this is that without additional information here, it's kind of hard to say what exactly is a particle independent of a wave. Like we have these things here that we can observe, and if you can affix something to a wavelength or a frequency or an amplitude, we can definitely say it's a wave. But if you can't do that, if you are observing something externally and all you have is velocities and energies and forces and momentums, that doesn't tell you anything. It's necessary information, but it is insufficient to determine whether or not something is definitely a particle or definitely a wave. And so we use one standard in science to discern whether or not things are particles or waves in their structure. And our cleverness has led us to some really unsettling places. Here's the cleverness. Here is the thing that particles have that waves don't. And this is a hard thing to figure out simply because it's not based on the property of one particle, it's based on the properties of two particles. The things that particles have that are special is that when they interact, what happens? What did we learn to calculate? What happens when two balls hit each other? What happens when I put a tennis ball on top of a basketball and I drop them?
They like transfer energy.
More specific, more conceptual.
Velocities.
They do what with their velocities? A tennis ball and a basketball are dropped together. What happens to the tennis ball?
They exchange velocities.
Yeah, and it goes fast.
They would exchange velocities perfectly if they were the same mass, but in general, they have a what? I'm looking for a word that begins with C.
Oh.
This thing can either be elastic or inelastic.
Oh, collision. I said that.
Oh, I'm sorry, I didn't hear it. When they interact, they collide. However, waves don't do that. When waves interact, they interfere. And despite the fact that most of these properties of waves and particles are held in common, this distinction right here, the fact that when two particles hit, like we learned to calculate in momentum, those two objects are going to hit off of each other, and then they are going to bounce back. However, when two waves interact, they are going to go through a process which we refer to as interference. So this is to say, and I'll show you guys a Wikipedia diagram of this idea first before I show you my hand drawing because it's prettier. If I have two waves in the exact same place and their amplitudes are lined up with each other, I get the diagram here on the left. This is called constructive interference. So two waves come at each other, but balls, particles, when they come at each other, they're just going to hit and bounce. Waves instead, they go through each other. That's why teaching is so hard, because if I'm trying to fill the room with my sound waves and one of your phones goes off or one of you has a side conversation with somebody else, your waves are going to interfere with my waves, right? And it'll be harder to discern that information. It's not like one person talking over another cancels them out. You can hear both people talking at the same time because the waves can pass right through each other. The way in which they pass through each other is going to determine precisely how they interact, this left one being constructive interference. So this is to say that if I play a sound wave into a tube and the tube bounces back that sound wave, according to this pattern on the left, it is going to make that sound way louder. But on the right-hand side, what do you notice about the two waves that are being added up down here at the bottom? One of them is at the top, but at the same time, the other one is at the...
Are you showing us something?
No, because I'm senile. I said I was going to Wikipedia.
Okay.
I'm sorry. So this one here on the left is constructive interference. I'm adding up these two little sound waves at the bottom, and because their amplitudes are lined up, we get this bigger wave at the top. That's called constructive interference. But on the right-hand side over here, what do you notice about these two waves? This one's at the top, but this one's at the bottom. So if you can force your waves to interact in this exact way, they just delete each other. One of the waves will completely destroy the other. Now, we don't see this with particles unless you're talking about antimatter. Like if I showed you, hey, a tennis ball comes at a basketball and they hit, and then now they both just disappear. How would that make you feel?
What?
Yeah, that would be problematic. You would know that you were either dreaming or for some other reason not in the right mind, because that doesn't happen with particles. Particles don't destroy each other. However, waves are allowed to do that by their physical properties. So when you have two waves in the exact same place, you get a superposition of those waves. A superposition. And these superpositions can take one of two forms. It can either be a constructive superposition or a destructive superposition. And in the constructive case, I have this wave being added up with this wave. They have the same wavelength and the same frequency. And the reason why we get constructive interference in this case is that those two peaks are lined up. So the outcoming wave has the same wave-like properties, except double the amplitude. If each one of these guys had an amplitude of A, now this guy has an amplitude of 2A. But in the case where we get destructive interference, the waves again need to have the exact same properties, except they are spaced out by exactly 1/2 of a wavelength. And because this one is at positive A at the exact same moment that this one is at negative A, positive A plus negative A is equal to 0. And both of these waves will destroy each other perfectly. Is this okay? Are there any questions about constructive or destructive interference? No? Okay.
No.
And now for the big brain part, the part where we get a little bit smarter and not just like learn a little bit of vocab. Here's some college level thinking for you. Let's go ahead and go back to our water wave generator. Whoop, right here. And so, wait, did I switch the screens over this time?
Yes.
Okay, I would hate it if I did more voiceover and still let there be nothing. Yeah, with our water wave generator right here, let's go ahead and see what this looks like if we have not one wave source, but two wave sources. So here I have two separate sinks that are going to drip side by side. And like I said before, when we do this, this is going to produce not just one of these circular waves, but two, where the top of the wave is that blue crest, and the bottom of the wave, the trough, is the black part of that wave. So now notice when these two waves come together, along these lines where they meet, right, we are getting some type of interference. You can see here in the middle, we still have that wave-like structure. So along that middle line, this is constructive interference. The waves are being allowed to coexist. But out here along these two radial directions, right, these two lengths, the wave is blurred. It's getting destroyed. That's because along those two lines, the wave itself is having destructive interference. And so on the opposite side, we get what is referred to as an interference pattern, where in the middle, the strength of the wave is stronger. But along these particular bands, the strength of the wave is weaker. Again, particles don't do this. If you send a bunch of particles into a room, you would have a bunch of particles bouncing around in that room. Because of the ways that these waves interact, the middle of the wave is stronger, and these edges of the wave are weaker, which is just odd. Is this okay?
Yes.
And here is an important note, though I'm going to, why this is an important note will become clear as we move along through these lessons. To have a pair of wave generators is physically identical to having two slits in a wall. So here's why I say that. This is just an experimentally easier way to produce the same physical occurrence, because when I send out a wave, the wave is going to get to the two gaps in the wall, and because it's being pushed through those tiny openings, like making pasta, right? it's basically going to be forced to restart at the wall. And this gap in the wall with these two holes is going to produce the same sort of source with two waves. And again, coming out on the opposite side, we get an interference pattern. Is this okay?
Mm-hmm.
Okay. So like I said, having two sources versus having a wall with two gaps, they're physically identical because forcing a wave through a gap makes the wave restart and spread out again from a single point. And so by taking advantage of this property, which we call interference, we have a way to test whether or not something is a wave or whether or not something is a particle. So this is to say, if I have some unknown substance, I can subject it to this quote-unquote double slit test, and depending on what it looks like when it comes out on the other side, I can then determine whether or not it is a wave or it is a particle. So the double slit experiment. What we just learned was that if I pass a wave through such a double slit, I have my wave, I have my wall with two holes. This wave is going to hit here and be forced through these two holes, and we're going to get a double wave pattern. And as this double wave pattern propagates towards some sort of detector on the other side, we are going to get a special stripy pattern, where in the middle it's bright, and then near that, nothing. And just so you know, the double slit pattern kind of repeats as stripes as it spreads out. It depends on how much space you give it. The more space you give it to spread out, the more stripes you will get in total. However, let's go ahead and imagine what would happen if we did this with a particle. So that is to say that I have my particle source, and for the sake of simplicity, let's just say it's a machine gun. And then I have a double slit, which is bulletproof. So no matter how fast or how powerful these bullets are, they won't destroy the properties of this wall. It's infinitely strong. And then on the other side, I have a detector measuring the incoming bullets. So I let this spray, and what happens to these particles as they go through this double slit? What does the pattern look like on the other side?
It's like two straight lines.
Yeah, you would expect either like two stripes to kind of match the exact pattern of the hole, right?
Mm-hmm.
So this is to say I send a bullet through, and here's where I'm going to disagree with you a little bit. Particles bounce, and these edges, they might be rough or whatever. So maybe there's a little bit of bounce as it goes through. There's a little bit of variation because of the hole itself. But I think no matter what, here we would get a bunch of points, a bunch of points, a bunch of points, a bunch of points. They would mostly be in the middle, right? Because we're assuming that these gaps are small and they're very, very, very close together. You're going to mostly get your hits in the middle, with a few that happen to hit weird and bounce out to the edges, but you're not going to get stripes. You're just going to get that most of your data is dead center, and then it spreads out as it goes out to the edges. Is this okay?
Yeah.
So the double slit experiment gives us a method by which we can differentiate waves or particles. I'm not going to get into the math of why what I'm about to say is true, but here's the math that you could use in order to generate what we would expect on these sides here. From first principle, you can use the rules of physics in order to show that what you would expect here is actually cosine squared of the position. All that does is it takes a cosine wave and it makes all of it positive, and it gives us that nice stripy pattern. Whereas here for a particle, this would give us an expected Gaussian on the opposite side, which is to say e to the negative position squared, centered at some value. But we would expect that if you did a histogram on this side over here, you would get a regular old distribution where most of the hits are in the middle, and then it spreads out as it goes outwards. Is this okay? So let me go ahead and mess your day up. What is light?
Both.
If you've been paying attention, you heard me say that it's both.
Yeah.
But let me go ahead and show you the experimental evidence why we know this to be true. Sorry, I thought I had this video queued up. I have the wrong video queued up. Oh my God, sorry, give me 1 second here. There we go, that's the stuff. Okay. So you can do this with light. You can take light and you can force it through a double slit. And when you do that, oops, sorry, wait, I want a particular one here. Yeah. When you do that with light, you need to do it with a laser. And when you do this properly with a laser, you can show that light interferes with itself. If you take a laser beam and you send it towards a double slit, and of course, if you're going to do this at home, wait, did I share it? Yeah. Right? Is this being shared?
No.
Eh.
Yeah, no.
Okay. You can pass laser light through a double slit. Now, if you're doing this at home, lasers are dangerous. Never point a laser at somebody's eyes. Don't toy around with lasers unless you know what you're doing. Red lasers are mostly safe. So if you were going to do this with a laser at home, do it with that. Like if you happen to have a cat toy laser.
Mm-hmm.
If you pass light through a double slit, it interferes with itself and you get that stripy pattern out on the other side. Now, the reason why you need to do it with light is that for this interference pattern to be obvious, the light has to be coherent, which means it has to be one color and it has to be in phase. Lasers are inherently one color, they are monochromatic, and they are inherently in phase, which is why we don't typically observe interference with white light. You can, though. There are certain cases where you get interference with white light, but it's rare because white light is a mixture of colors. It's a mixture of phases. But these funny patterns that you get from lasers, all of this is indicative of the fact that the light that you have been viewing your entire life has been a wave that is capable of interfering with itself. Is that okay?
Mm-hmm.
Okay.
Mm-hmm.
However, what gets really interesting is what happens when you do this with electrons. What is an electron? Tell me what you guys know about electrons. So just so that you guys know, photons, which is to say light, exhibits both wave and particle features. The part where light definitely shows interference is it exhibiting a very, very wave-like feature. Exactly how it exhibits particle-like features is a discussion for another time, I suppose. But what do you think an electron is, based on your education from chemistry?
It's like negatively charged.
Negative charge. Yeah.
It's a negatively charged what?
Atom.
Particle.
Oh, never.
Atoms are collections of protons, neutrons, and electrons. They're pretty big. But yeah, you were taught that an electron is a negatively charged particle on the outside part of an atom, and for some reason they live in sets of 8. So if you were to do this with an electron, which of these outcomes would you expect to get?
The right side.
If electrons are indeed negatively charged particles, you would expect that you should get this thing here on the right-hand side. You should get a Gaussian. Now, let me go ahead and show you the experimental data from the 1940s of exactly what happens when you do this exact experiment with electrons. And this is the experiment that absolutely ruined physics. And I mean by that, it's super interesting and it's crucial data, but let me ruin your day. My screen sharing the right screen? Do you see the black screen?
Yeah.
Okay. So here's what happens when you do electron buildup. I send an electron gun, like in the back of one of those old TVs, through 2 openings. You can see them on the screen here, right? All these dots.
Mm-hmm.
And so we're getting dots, so that means it's a particle, right?
Mm-hmm. Yeah.
Just keep watching.
Mm-hmm.
So we're not sending more electrons. This is just the buildup of the data over time. At the beginning, that was the actual time. These are being sent pretty slowly, literally 1 electron every few seconds. However, if we let this build up for a long time, what do you notice starting to happen? What do you see there?
There's like those collections, like lines.
So originally, we were receiving these electrons one at a time, right? A series of little pinpricks of light. But as we let them build up, even though each one of these electrons arriving is obviously a particle because it's arriving at some set point, if you let it build up, it gives back stripes. Y'all see that?
Mm-hmm.
And like I said, this is actual experimental data. This is, I think, from the Mitsubishi Corporation in 1950, right after World War II, like right after Reconstruction, when they started getting people back to research work. This is one of the first things done there. And you can see here that on one hand, every object that arrives is a speck. Each object that arrives arrives as a particle. But if you let it build up, it makes the wave pattern. So tomorrow, I'm just going to give you the answer that took us, a century to arrive at. Electrons also exhibit both particle and wave-like properties. They arrive as particles, but if you let them build up, they give you back the same pattern that waves would. And in fact, what quantum mechanics teaches us is that at that size scale, if you were talking about things that tiny, everything has particle-like behavior and everything has wave-like behavior. Which one you use depends on the context in which you are talking about the object. Tomorrow, I'm going to give you guys the punchline on how exactly electrons exhibit properties of particles and waves. And to end this, I want to show you guys a quick demonstration, which is kind of unrelated to the rest of this stuff. It's another trick that you could do with light at home, which is a quantum mechanical experiment that isn't just that laser that I showed you. The thing with my sunglasses, which I'll post a follow-up video too, in case you would like to learn more about these topics. So here's the flashlight from my phone. It's bright. These are a pair of polarized sunglasses that I use for traveling. And I'm going to go ahead and I'm going to take the cell phone and I'm going to put that behind the lens here. These are my dorky sunglasses that I use when I'm running because they're aerodynamic. They are also polarized. And so go ahead and look at what happens when I stack these 2 lenses up. And then I take one of them and I rotate it. What do you notice happening to the brightness of the light?
It's like getting
Smaller.
Yeah, so you'll notice when I put the 2 lenses to 90 degrees, right? If I put them 90 degrees in their original position, this blocks most of the light coming through. And then when I put them parallel to each other, it lets basically all of the light through, aside what's being blocked by the plastic. So the brightness here, the amount of light that escapes itself, is based on the relative angle of polarization. At 90 degrees, none of it goes through. At 0 degrees, all of it goes through. This is a quantum mechanical property, and I'm going to post an interesting video about it in the classroom in case you want to keep learning even though school is over. Y'all have a nice day, and I'll see you tomorrow.
Thank you.
You too.
Mm-hmm.
Thank you.